Welcome back, everybody. It's now my great privilege to introduce the second speaker of our conference, Daniele Oriti, who is going to tell us more about the many quantum and gravitational challenges to Humeanism.
We know it's there.
Can you point at the audience, but not at the screen? Anyway. Okay, so thanks to the organizers for the invitation, first of all. I will illustrate a number of challenges that I think modern physics poses to the humanist conception of the laws of nature. And there will be at several levels. So let me first summarize how I understand humanism. So there is a general ontological picture underlying this view, which is that there is a Humean basis of non-model facts, and then laws supervene from that, or on that. This Humean basis is a distribution, organized distribution of fundamental intrinsic properties over space-time, characterized by no necessary connection, but as I will discuss in a second, as it has been pointed out by a number of other people before, from which I've learned, the world-making relations are actually space-time relations. So space-time is really central on this, in this Humean basis. So there is a sense in which laws are derivative on facts, because they supervene, but they are still objectively out there, and this is a central point in this view. As a key part in this supervenience is the best systems account. So the idea that laws of nature are identified as propositions in best systems, so some true deductively closed theory that balances in the best possible way simplicity in expression and strength in explanation. Again, the key point is also this best system exists objectively independent of agents out there. That's why it's a metaphysical position and not just an epistemological position. Underlying there is a broader view from you is of what facts are and how they are characterized. And this is even before you talk about laws. So there is the idea of the concept of a possible world, which is a spatial-temporal arrangement of local quantities. And by the way, and on this summary I'm based, it is based on the paper by Vincent and Chris, which I would like to point to, but it's there. Anything that is incorrect, it probably is my misunderstanding of that paper, but feel free to ask to me. If I know the answer, I will reply, otherwise I will point to Chris and Vincent. So, as I already said, space-time is actually the backbone of a possible world, because it's spatial-temporal relations that unify and isolate the worlds. More specifically, you can identify the way in which space-time enters in this Humean mosaic of facts and in the definition of possible worlds. So there is an assumption of separability, which is basically an assumption of locality. And the second assumption of statism, which is basically the statement that what the facts are determined by the total physical state of the mosaic. It's a sort of autonomy assumption, so there's nothing else that you have to bring in to determine the facts. It is related maybe to some form of determinism, so anything that happens that you see as a fact is determined by what is in the mosaic itself. But again, the end point is module a bunch of other details, is that space-time and locality are central notions in a very metaphysical ground for understanding what laws are. In fact, in this account, you can separate two steps. You can distinguish two steps. The first step to identify this non-model basis of facts. And then you have to add some recipe for reduce every model notion to, and in particular laws of nature, to this basis. These are two separate steps, and graphically are pictures the story like this. So there is a human mosaic of facts there. Laws that are encoded in best systems supervene, but it's also the statement that you can reduce those laws to the human mosaic. So in a sense, it's a situation in which emergence is compatible with reduction. Now, modern physics will challenge, in particular, the human mosaic as it is currently understood. One can have some general philosophical challenges to the very idea of laws as described in this best systems account, and I will in fact start from that. But quantum gravity and quantum mechanics mostly challenge this first part, the basis. And most of the talk will be about this second aspect. Let me first start from a bunch of comments about this best systems account. I will be very brief because it's not my main point here, but I want to discuss it for completeness. And it has to do with a perspective one can take on the traditional challenges of this account, which have to do with what you actually mean by simplicity and explanatory power. Can you be more precise? What do you mean by balancing them? What do you mean by the best system in some absolute sense that will balance them? And then the objectivity of this account. So the best systems account in fact dates back to Mill, and it is later, as I said already, discussed by Lewis in this more modern form of finding the best combination of simplicity and strength. And it's important once more, there's a non-epistemic account in this formulation because it applies to known and unknown systems. It doesn't start from necessarily existing accounts. In principle, the virtues of that, it captures some sense of generality of what laws are, which is a key point of what we would like laws to be. It's, at least on paper, connected to scientific practice and faithful to observations and facts in the empiricist tradition, because that is supposed to be how we determine what the facts are. They are supposed to be in origin facts of experience. And the difficulties are, to a large extent, what I already mentioned, how to measure and then balance the simplicity and strength. How do you achieve any objectivity in this type of balance? How do you compare different systems? And so on. So these are the epistemological challenges that gave a good reason for improving, in the view of these authors, the account to the better best systems account. And I would say that the way in which it has been improved by Callender and Korn, it resonates also with the ideas by Hall, according to which the best system is determined by epistemic standards that determine the nomological possibilities for the non-model facts, which are operative in science. So it really tries to answer those, to tackle those challenges, looking at science, looking at epistemic standards. And my point here, and then I move on, will be basically that this is really an epistemic term, and it somehow is admitting that the ontological commitment and the metaphysical step is not really grounded in itself. It's really an extra step, but the basis for that step is just epistemic aspects. So this suggests, at least to me and a few others, that what is really going on when you move to the better best systems account by Cohen and Callender is that you really realize that these epistemic elements are essential, and they are what identifies a law as a law. Which means that you start accepting, I feel, that laws have an epistemic nature, not an ontological nature. And of course this relates to the general issue of realism, scientific realism, and you can see that even better in this quote that I'm currently pointing at, the last one by Cohen and Callender, which in fact discusses what sort of realism is compatible with this better best systems account. But again, this will not be the main point in this talk. It's a different level of challenges to the humanism for laws. Let me move to science. So the challenges coming from quantum gravity and more generally from quantum mechanics have to do, as far as quantum gravity is concerned, both with the idea of the human mosaic, the facts forming the human mosaic being localized and connected in space-time, so the space-time grounds for the human mosaic, but also with the objectivity of those facts. The general quantum mechanical challenges are more directed specifically to this objectivity of facts. So let me take them in turn. They are of course related to the traditional challenges from quantum mechanics to humanism. They are also summarized in the paper by Vincent and Chris, having to do with entanglement and Bell theory and Bell theorem. And you will normally summarize them as saying, well, quantum mechanics is non-local, and this goes contrary to the separability ingredient in the human mosaic, so the locality. And it's quite correctly pointed out in the same paper that the dismissal by Lewis that doesn't want to take lessons from quantum mechanics until he drops some instrumentalist attitude is, apart from being short-sighted, if you are really committed to naturalism, or empiricism, then it's a bit misplaced, because this non-locality characterization of the consequences of Bell theorem and entanglement follows from a strictly realist position about quantum mechanics. In fact, the alternative attitude that people take in face of Bell's theorem is to weaken realism in order not to weaken locality. So I find that a bit misplaced. In the same paper, they mention possible solutions that have been suggested to meet this challenge from quantum non-locality and entanglement and quantum correlations. One is simply to add to the human mosaic more global facts, so non-local, so in fact accepting the statement and dropping the strict requirement of locality in the definition of the human mosaic. Or to replace physical space with configuration space, and then ask for locality in configuration space, in some sense. Now, concerning this, I will develop this point later on, because it's one of the central ones I want to make coming from gravitational physics. But in classical continuum physics, this suggestion by Lower is in fact consistent with the relational strategy. It amounts to that, because the relational strategy to the construction of observables, which are gauge invariant in gravitational theory, is really the statement, ultimately, that physics is in correlations on configuration space, not on the underlying manifold, which is just this mathematical structure that is very convenient, but that's not where the physics takes place. And space-time itself is defined as a subset of such correlations. I will try to be a little bit more specific about this later on. However, the suggestion was made, and I just said the suggestion is actually correct in light of classical gravitational physics. More problematic at the quantum level, but let me get to that. But it's funny, because this suggestion was actually made in the context of particles moving on a space manifold. So in that context, I would say the suggestion doesn't really make too much sense, because there is an underlying space-time manifold that is part of the ontology of your theory, and you are not dismissing it because of diffeomorphism invariance. But the challenges I'm going to discuss are the following, summarize, and then I start discussing them. There is a gravitational challenge, classical and quantum, which is that relational physics, when you take on board this idea that you construct invariant observables not relying on a manifold, but in relational language as correlation between field values, well, this becomes fundamentally perspectival. And any notion of objectivity should be expected to be approximate only. That's the first claim. The second, coming from quantum gravity, is that space-time is not fundamental, whether understood in this relational language or understood in terms of a manifold, even less. And then is a big challenge to humanism coming from quantum gravity. And then there is the more general quantum mechanical challenge that, according to some results and some interpretations of those results, then realism itself has to be a bit relaxed, and the objectivity of facts has to be relaxed too. So that, of course, is a direct blow to the standard initial formulation of the human mosaic. Okay, so let me discuss these challenges in turn. I start with the quantum gravity challenge, aiming at this idea of facts localized and connected, organized in space-time. I'm not going to argue for why quantum gravity suggests that space-time is not fundamental, so that I cannot be accused of giving always the same talk, because that's a point I made a number of other cases, and okay, by now I'm tired myself of repeating that. So, okay, let's say that some approaches to quantum gravity, for better or worse, replace any standard notion of space and time as formulated in gravitational physics, in terms of classical quantum fields, initially defined on a manifold, with other type of structures. So in this sense, because that's how we normally understand space and time in terms of fields defined on a manifold and their relations, the kinematical structures in quantum gravity are not going to be spatio-temporal, if those suggestions are correct. The dynamical processes are not going to be spatio-temporal, in that sense. There's a bunch of other potential issues that I'm happy to discuss, but will not be central here. This, of course, is a problem that Vincent and Chris focus on in their own paper, and they focus some possible proposals for how to deal with this challenge. So somehow separate free dynamics from anomic, free kinematics from anomic dynamics. You can separate, that's another possibility, separate the space of possibilities and say that that corresponds to some Hilbert space that is in itself not defined on space-time. And you have to separate it from physical space, which is something else, which you have to reconstruct. That's a possibility. And further proposal mentioned in the paper by somebody else is that this entanglement includes non-locally in space the facts, again to account also for the quantum correlations which are seemingly non-local in space. I mentioned here again that there is a related empirical challenge. In origin, the human mosaic comes from the regularity tradition and from the empiricist tradition on laws. Those facts are facts of experience to start with, are stuff we observe. And however you modify and you identify differently the human mosaic in quantum gravity, the results are not going to be directly facts of experience. So that type of empirical challenge, so to speak, is of a different type and will stay regardless of what I do in the following. So what do I do in the following? I discuss some work, some ideas we presented and discussed with Vincent in a another recent paper. And we just ask ourselves, okay, if these are the structures that quantum gravity gives us, and I'll discuss what they are, in what sense they can be represented new human mosaic? Can they provide seeds for laws to be there? And what sort of facts are we dealing with? What sort of structures are we dealing with? And my main point would be that you can identify a number of properties, number of features in these structures that can provide seeds for laws, replacing some key ingredients in the traditional human mosaic, and they are distinctively of a quantum information theoretic nature. That's the message. The rest is explaining and justifying a bit more the message. So the idea would be that somehow quantum correlations as concepts are more fundamental than space. You can identify quantum correlations in quantum gravity even if you remove any reference to space. And in reconstructing notions of space, in fact, there is some primitive entanglement geometry correspondence that you can rely on. So there is a notion of gluing facts in the human mosaic, but without space-time, and in fact is going to be entanglement without space-time. So I'm taking on board one of the earlier suggestions. And the dynamical processes that you also identify within this type of structures are of similar information theoretic nature. If there is any nomic aspect, I'm not really sure that I'm happy with this notion of nomic aspect. If it is more than constraining the possibilities at an epistemic level, that's a different discussion. It's going to be in some overall constraints on the states and histories of the theory. I will also suggest that these information theoretic aspects, which I'm going to show are central in the definition of these quantum gravity structures, also suggest an epistemic perspective on laws, rather than a metaphysically committed perspective. So you can still apply the idea of laws as theorems in our best quantum gravity theoretical system. Entanglement relations among quantum gravity microscopic and fundamental degrees of freedom will be the new human mosaic grounding laws. But the theorems in these quantum gravity based systems will be about theoretical entities and will be severely underdetermined by observations. I'm not sure I want to enter the discussion whether this is a problem or a virtue, but I will just argue it's a fact. The moment space-time emerges, and it has to emerge in some approximation from the collective quantum dynamics of this, in fact from the quantum correlations of these pre-geometric non-spatial temporal structures, well, then you will have a similar emergence of the traditional human mosaic from the quantum gravity human mosaic that may have this type of features. That will be a little bit more specific without giving too many details. Well, I will show some details and you're welcome to ask, but I will not insist too much on the details. In a broad range of approaches to quantum gravity, canonical loop quantum gravity, spin-foam models, which the propaganda calls covariant loop quantum gravity, in tensorial group field theories, in lattice quantum gravity with particular choices of variables. These are the type of fundamental states. They are associated with graphs labeled by group representations. They are the so-called spin networks. So they're just algebraic data on a graph, on a network, on an abstract combinatorial network. What I'm going to say, what I'm going to show you in the following, with a few technical points, is that you can understand this type of structures in the language of quantum many-body systems as assigning a Hilbert space to each node on the network, and then establishing an entanglement pattern across these bodies, these Hilbert spaces. So this single body Hilbert space is the Hilbert space that you associate to a quantized tetrahedron, abstract tetrahedron. course, I'm glossing over 20 years in which people constructed that and argued why it's a good choice and blah, blah, blah. But let's take it as a Hilbert space. That's the graphical, pictorial, and potentially physical representation. There is a notion of geometric operators at this discrete level of areas and volumes that act on this Hilbert space. You see, I mean, in any case, we're not talking about smooth manifold with fields and so on. It's a combinatorial algebraic structure there. And the generic state is going to be some collection of such quantized tetrahedra. The next bit is that you can take the Hilbert space of two tetrahedra, look at the subset of degrees of freedom associated to the triangles of those tetrahedra, and then establish that the relevant state you're going to consider is a maximally entangled state between the two states of two tetrahedra along the degrees of freedom of the to-be-shared triangle. You take those degrees of freedom, you impose that you only look at maximally entangled states of that two-body system along that subset of degrees of freedom, and then geometrically you can compute operators and so on. The resulting state has the interpretation of having taken the two tetrahedra and glued them along the shared triangle. And you can keep going with the process and you build an abstract graph or a simplicial complex with many such tetrahedra as an entanglement pattern. You decide which subset of degrees of freedom is entangled. And you get a spin network state. So there is an even more primitive structure behind the spin network states, which is this one. And as I already said, these are the states of a number of quantum gravity formalism. So let's take the suggestion. So it's obvious that there is an immediate entanglement geometry correspondence, but it's more like an entanglement topology correspondence or connectivity. The notion of a lattice of a simplicial compass is a pattern of entanglement in a particular quantum state. But then you could go a little bit further. You can ask, okay, I have a notion of area for a triangle, and then you ask, okay, that's associated with the triangle, that's where I have some entanglement between the degrees of freedom of the two tetrahedra. And then you can actually show that the measure of entanglement scales, the amount of entanglement scales with the area. So you can invert the logic and say, okay, area is nothing else than the measure of the entanglement associated with that triangle. And you can do the same story with the volume of each tetrahedron. The measure of entanglement across the degrees of freedom associated with the four faces, the four triangles of the tetrahedron, scales with the volume of the tetrahedron. So again, there is an entanglement geometry correspondence that you can use in reverse from the quantum correlations to reconstruct geometric notions. Furthermore, but I'm not going to discuss much about this, you can take a spin network state and treat it as a quantum circuit. In fact, to use it to define maps from boundary, from a subset of degrees of freedom on the open links on a boundary to another subset as a quantum channel transmitting information from one to the other, one subset to the other. This is a standard definition of quantum channels. And there's a little work about that, you can be more precise about this. So the message is, well, you take the fundamental structures of quantum gravity at least at this kinematical level. We are not talking about histories or processes. And what you find is that you can fully characterize them as quantum circuits in quantum information theoretical language. Quantum correlations are what builds them really in their connectivity and gives them some proto-geometric interpretation as well. So it's really, if these are the facts, you found the glue, and these are quantum information theoretic. That's the point. At the level of histories, you can rephrase, this is not very common in the spin foam literature, but you can rephrase the histories of those states, which are the spin foams, in a very similar quantum information theoretic language. You can distill what the possible process is as a set of events, put it in quotation marks, and some order relations between them. So it's a directed graph. in the simplicial geometric setting, which are tetrahedra evolving, forming simplicial complexes, there is a restriction on the valence of those nodes, but the structure is of the same type. It's a directed graph. Notice it's not a causal set. A causal set would be this type of structure, common to any spin-form model, with the additional condition that there's no closed time-like loops. So it's not a directed graph, it's an irreflexive directed graph. And you can take it as a special case. Among all the possible spin-form complexes, there will be those in one-to-one correspondence with causal sets. Also, these histories, these processes, non-spatial temporal processes, can be decomposed in building blocks, and you can go to the quantum level and construct what is called quantum causal history by assigning Hilbert spaces to the links, oriented links, and some elementary evolution operators to the nodes of this history, the events. All current spin-form models can be written, and it's a general recipe, in this type of language. You take a directed graph, you associate an operator to each event, to each node, to each vertex of evolution, and to each link you can assign some additional gluing-like or propagating-like operator. And the amplitude associated to the whole complex is that one, the one roughly in the middle, the AM. Is some way of tracing all these operators together, given the Hilbert spaces you assign to the indices, to get a complex number. That's a probability amplitude in the standard sum over histories interpretation, the formulation of quantum mechanics, path integral like, associated to each possible process. The full dynamics will be given by sum over all possible processes. And the sum is both over the combinatorial structure, number of events, how you connect them with directed links and so on, and the possible assignments of quantum data in the Hilbert spaces. All quantum gravity models in that category that I discussed have this type of structure for the dynamics. Now, it's a general result that if you have quantum causal history of this type, and you want to say that it admits a unitary evolution between acausal surfaces, well, this is translated, can be translated exactly in the language of quantum circuits. So it becomes a quantum computational network, mathematically. Let me skip the rest of the details. For this to be true, you have to, first of all, not have closed time-like loops. So it's only a subset of quantum causal histories that has this property. Second, the evolution operators that you put everywhere should give rise to unitary evolution. Both these conditions are non-trivial. Let's look at the unitarity effect. You can write down a bunch of conditions that the assignment of operators to your quantum causal history should satisfy to have this unitary evolution. But you can show that if the history defines a computational network, so it's a unitary, some unitary evolution, then the full dynamics with the sum over histories does not. Or you have to try to impose the conditions on the full dynamics, and then you have to relax the conditions of unitarity and from the individual histories. Something similar happens regardless of the absence of closed time-like loops, because you can identify the possible strategies for making the causal loops, which are in principle there, irrelevant. Either you modify the dynamics to exclude them, or you modify the dynamics to suppress them, because they are there, but maybe they contribute in a negligible manner to the full theory, to the full dynamics. Or you only allow harmless causal loops from the information theoretic point of view. Okay, these are all technical details. The point is that, in principle, you can find conditions for having a proper causal evolution, and also the condition for having a proper unitary dynamics. The fact is, all current spin-form models do not satisfy those conditions. You can reconstruct, you can modify them so that they satisfy those conditions, and this has been done by at least one very clever person in 20 years ago. And that's Ethera. And then more recently there's been a bunch of other papers doing the same thing for other models. But it's exactly the same idea. But that procedure is very much ad hoc. We don't have an in-principle construction that will give us unitary causal evolution in spin forms. And it's a fact. Okay, so before I move on to the other challenges, I told you that all the fundamental quantum gravity structures suggested by these quantum gravity approaches are information theoretic. They are quantum information theoretic. So, if overly excited, you can proclaim that, oh, but then the universe is a quantum computer. And you find claims like that in the literature. I would take a different attitude, and let me explain it. I would start from a more epistemic view on physical laws and a more important role for agency in constructing our models, in understanding what laws are. From this point of view, I mean, if you take this point of view, it has some implications for how you see the models we construct, even the fundamental ones like quantum gravity models. And I would even say that you would think naturally that the universe is largely what we think it is, but in the sense that, not that we got it right, but that it's a more active sense. You know, there is a sense in which we make the world when we think about it and we organize it in mathematical physical models. Again, I'm taking this epistemic attitude as a starting point. And then you will let to think that our models, so the structures we see in the world looking at our models, will somehow resonate or reflect the way we think because of this. And the main point is that once you remove space-time notions, and we have to think about the world without space-time, we are left with combinatorics, algebra, and abstract information processing. That's how we think. Quantum computers are just abstract models of quantum information processing and therefore our own reasoning. And so the universe is largely what we think it is, and we think like computers, because better phrase, that is actually computers that are built to reflect to some extent how we think. So this quantum universe is naturally modeled as a quantum computer, even more in this space-time less context. Anyway, so I move on, now let me skip on this. There's more to be said about this epistemic attitude in the context of quantum gravity, but I'll skip that. Let me move on to another gravitational challenge, which has to do rather with the objectivity of facts. It has to do with all the relational construction for gravitational observables, invariant, diffeomorphism invariant observables, well encoded in the citation from Einstein that was in the previous talk. So the thesis is the following, that once we take seriously the distinction between open and closed systems, and which is in fact encoded in the presence of finite space-time boundaries in our models of gravitational systems. And once we take seriously the need for physical reference frames, and that is encoded in the fact that we are forced to work with gauge invariant quantities, and gauge invariant observables in GR are non-local, are spread over the whole manifold, pointing to, in my view, to its non-physical nature. We have to conclude that there are serious obstacles to a framework that is completely intersubjective, and there are fundamental limits to a notion of strong objectivity. Now I will argue for this rather quickly. The presuppositions of this argument is that any modeling starts with a system agent or system observer split, and that the system itself is also to be modeled in its, if the system is to be modeled in the spatial temporal properties, then the existence of such split translates into some boundary of a region occupied by the system. It's a finite boundary. That we can also include aspects of the observers in our models. In particular, we can include, and maybe we should include, the reference frames that the observer uses to localize systems in space and time. to give meaning to the notion of space and time, clock and rods. And if reference frames are to consider part of the reality, their physical properties should be accounted to. Okay, now the argument. The starting point is we do localize systems in space-time in terms of points and trajectories on a manifold. We make them explicit in terms of coordinate frames. That's the status quo. However, diffeomorphism invariance implies that coordinate frames are entirely unphysical. And in fact, even manifold points and directions and paths may disappear entirely from a more fundamental formulation of the theory. Although, of course, they are useful, we use them all the time. And I can give a number of examples for why this is necessary, but also examples in which this is actually realized. We get rid of the manifold and definitely we get rid of coordinate frames. Localization in space and evolution in time are in fact relational and require physical frames. So observers use physical, normally material, clocks and rods to define space and time, and physical observables are best understood when you take this fully into account. Physical observables should rather be understood before any approximation as a relation between dynamical fields and the material clock and rods, which are other dynamical entities that are used for their localization in space-time. Any quantity constructed like this is entirely non-local with respect to any supporting manifold. But that's not a bug, it just tells you it's not the manifold that really defines locality. But however, if you're serious about this and not just you accept it with words, well, you have to realize that truly physical systems are very different from coordinate frames, physically. They are fully dynamical. They interact with the other dynamical entities. They back react on geometry through their own energy momentum tensor. And they're also quantum. My clock ultimately is a quantum system. So before I take approximations, they are subject to superposition in the same values that define my time. They are subject to quantum fluctuations, entanglement, contextuality, you name it. Coordinate frames, as we normally use them, arise, and again, one can give examples, in idealized situations in which we basically neglect all these physical properties of our physical reference frames. And there's nothing wrong in neglecting them whenever it's appropriate. But from a more foundational physics point of view, we have to keep track of the fact that that's an idealization. There are cases in which coordinate frames become physical, in particular if you take asymptotic boundary conditions and diffeos do not act on the boundaries. But these are also idealizations. Based on what I said earlier, removing this idealization means that you try to work seriously with finite regions and boundaries at finite regions. And research on this gravitational systems in finite regions tells us that we have to endow boundaries with dynamical edge modes, additional degrees of freedom on the boundaries, so to maintain full gauge invariance. And these edge modes themselves can be used to define physical frames. So we are back to where we concluded earlier. At the end of the day, we're going to have physical frames everywhere, and only physical frames. Now, a physical frame is partially the embodiment of an agent, of the observer. Any relational observer will, in general, depend on the physical frame you're using to define it. So, gravitational physics is intrinsically perspectival from this point of view. It relies and depends, is formulated on, depending on particular physical frames you pick up. We do not know currently if there is any notion of physical general covariance. So a map that doesn't leave anything behind of the different descriptions of physics you obtain fully in terms of physical reference frames, beyond the idealized situation in which you approximate them with coordinate frames. Because in that case, we have the standard general covariance, and we are fine with that. There are a number of arguments that can be given for why there should be some form of physical general covariance. On the other hand, we have a number of arguments saying that even if we have full physical general covariance, this will not indicate complete invariance of physical properties. A number of physical properties, as read out of different frames, will stay different. And I understand in this context at least a physical general covariance requirement to be a requirement of complete intersubjectivity. So you can always translate from the perspective of one observer to the one of another, from one subject to another, without leaving anything behind. Everything can be translated. But the fact that there are no necessarily invariant quantities under that, or invariant facts, means that we have an irreducible limitation to a notion of strong objectivity, going beyond this intersubjectivity, this translability. So that's one argument, and this challenges the idea of objective facts and of experience from a classical and quantum gravitational perspective. 5 minutes?
We have about 12 minutes left, including Q&A.
12 minutes? You're super generous.
No, with Q&A.
Ah.
I'm not as generous as I seem.
I take it back. I don't want him as a general anymore. Anyway, I'll be quick.
Yes.
I'll try to be quick.
I'm informed by informed source that we can take some more minutes.
It works like with Italian bureaucracy. You just have to insist. Okay, until you get some answer that is a bit more convenient. Okay, so let me go to the very last part. No gravity anymore. Just quantum challenges, and they have to do with the idea that facts are relative in a certain sense, and I'll try to discuss. They all can be traced back to the Wigner's friend thought experiment, which you have some observer inside the lab, and she happens to be a friend of Wigner until this thing was set up. Afterwards, I'm not sure. And she measures something. She has a two-level system that she prepares in a superposition state. And when she measures the system, she will get one result or another with a certain probability, and after the measurement she will say, oh, if I got result Z plus, then my state is the state in which Z is the definite value plus. Wigner is outside the lab, doesn't measure directly the system, although in principle it can in a number of ways. So it assigns a state to the whole system of two-level system plus friend or plus lab, which is a superposition of the two values. Assuming that the measurement has taken place, he assumes the state to be a coherent superposition of two states in which the friend and the two-level system are entangled and perfectly correlated. But in general, you have still a superposition because he doesn't know what result the friend got. In the slightly refined version, the friend is allowed to tell Wigner that in fact the experiment has taken place, the measurement has taken place. So by sending a message, you add the degree of freedom of that message that conveys the information. I have observed a definite outcome. But still you have a superposition of states, and there's no definite outcome from the point of view of Wigner. He only knows that there is some outcome according to the friend. Okay, so here in this type of situation, the challenge is that in this framework, you will be led to say that, well, there is a fact of the matter for Wigner, and there is a fact of the matter for the friend. These facts coexist. They are there. Again, and so you ask if there is a theoretical framework in which you can have observer-independent facts in the sense that you can assign jointly truth values to every possible observational statement. 0 or 1, I mean, including 0 or 1, true or false. Some facts do not happen, but they have a definite truth value. So one fact is the friend as measured z plus. The other is the Wigner as measured phi. So indeed the state is that one that he was assigning. These are the two different facts. Again, it's obvious that the point is not so much what happens when Wigner performs another measurement, a further measurement, either on the full system or on the two-level system. Or to put it more simply, just ask the friend what the result was. In that case, we know what happens and there's no problem. There is a stronger condition. You expect an assignment of truth values to the statements independently of which type of measurement Wigner further performs. If you measure directly the two-level system or again the global system of lab plus two-level system. So is the statement that there is a Boolean algebra containing all the truth values of the propositions for all observers in this scenario. So this is what one means by observer independent facts, and I'm using results and based this on the paper by Bruckner, on a couple of papers by Bruckner, and in turn by a paper by Fraukiger and Renner. So a theorem by Chaslav Bruckner basically states that the following states are incompatible. One is the universal validity of quantum theory, assuming therefore that quantum mechanics holds at any scale, you can apply to the whole lab, to the observer, and so on. Second is locality, no influence of what people do in different regions, no consequence for the outcomes of their observations. There is freedom of choice. Wigner is entitled and free to choose different type of measurements. And this again is no further constraint, so they are statistically independent. And then the observer independent facts in the sense of the Boolean algebra I mentioned earlier. I'm not going to, of course, to the proof, but the point is normally all this is normally done in the context of an extended Wigner-friend scenario with different observers, different friends, and different Wigners. Now, without discussing much, the point is the following. The conclusion of this theorem, taken at face value, and then I mentioned a number of objections. Even if Wigner has evidence for the occurrence of a definite outcome in the friend's laboratory, he cannot assume any specific value for that outcome that to coexist with the directly observed value of this outcome. And there's no theoretical framework where one can assign jointly the truth values to observational propositions of different observers under these assumptions. So they cannot be facts of the world per se, but only relative to observers. That's the conclusion that Chaslav and others take from this result. Now I'll skip on Fraukiger-Renner theorem and related. They all have to do roughly with this story, with this type of conclusion. Let me skip this. A further way of refining the conclusions is that you have to differentiate between one's knowledge about direct observations and one's knowledge about others' knowledge that is compatible with physical theories. Again, things are related to observers and not necessarily common to some abstract third-person view. Okay, let me mention a couple of objections from Emily about this, so that there is already some more material for discussion. Like any no-go theorem, you have to check exactly the assumption, the definitions of what is meant by relativity of facts and so on. Again, I only use a few seconds here. So it's important to distinguish exactly what type of differences, lack of agreement between observers and about the outcomes of their observations can be shown based on those theorems. That's one point. I don't want to go there, otherwise there will be no time at all for discussion. And one can argue, Emily argues that the type of disagreement found in these no-go theorems doesn't necessarily have to imply any radical non-objectivity of facts at a stronger metaphysical level. And you can adopt a deflationary interpretation. And in particular, a key point, and I'm summarizing, I apologize for summarizing in 30 seconds, but there is a key point, which is that one can and maybe should distinguish between intrinsic states of a system and so-called interaction states. The interaction states being the one that you basically encode the probabilistic results of and the predictions of observations you can make upon interactions with the system. And the intrinsic states are somehow, they encode the intrinsic conditions, including the conscious experience of an observer which has witnessed a particular result. And again, it's the noble theorems, that's the conclusion by Emily, if I understood correctly, is that they do imply some relative nature of facts, but they have to do more with the relative nature of these interaction states, rather than with more stronger ontological nature of facts. But in any case, they do pose challenges to intersubjectivity in their terminology, and so we have to take them seriously into account when we try to make statements about what are the facts, what happens when you observe things, and you make up theories about that. Okay, so I'm just saying that this idea that no, you should take that seriously on board and relax this independence from observers of facts is in line with a number of interpretations of quantum mechanics, which have a bunch of problems on their own, but at least this one is sort of natural, which indeed point to something that are based on some more epistemic view on quantum states. They suggest a different type of metaphysics based on somehow the active participation in making reality of observers, participatory realism, I would call it, and indeed a perspectival notion of objectivity on which we should base our epistemology. Now, the main point is that all of these each of these ingredients is work in progress very much, and this applies to everything I said earlier, including all the quantum gravity story. I mean, quantum gravity and quantum mechanics make a number of very radical suggestions about physical reality, about space-time, and then, therefore, about laws. And that's the first message. I would argue that all those suggestions push in a direction of a more central role for epistemic elements. But all of them are very much work in progress and present big challenges to much of standard epistemology and metaphysics. These challenges are not necessarily imposed on us. We may decide that the challenges to standard metaphysics and epistemology and so on are such that we better dismiss those suggestions rather than embark in that revision. But I would instead saying that deflating those suggestions and avoiding the challenges may, apart from creating even bigger challenges, more importantly, may mean missing out on something truly important and in fact very interesting and quite fun. I didn't love it, but I think it's quite fun. Thank you.
Thank you. We're going to take a couple of minutes for questions, so please raise your hands if you have a question. Enrico, why don't you?
Yeah, thank you, Daniele. Very quick. I was just, among many things, I was curious about, so something you said about general covariance there, where you said that there's no physical version of general covariance. I was sort of curious to understand exactly what you mean by that. And I just wanted to give a quick example to try to figure out if, like, you can this as physically general covariance or not. So people have been working on these constructions of like operator algebras for simple spacetime. In particular, this construction they use something that's called the cross product, which is basically it ends up being something that sort of looks like a product of an observer's algebra with the algebra of the simple spacetime, and one uses that to have a notion of time and to be able to define meaningful notions. And one interesting thing about the whole construction is that there is a further sort of toy in there, a sort of small gadget in there, which is called the Conco cycle, that allows you to basically prove or show that any choice of representation of the real line, so any choice of observer that you can make, of block that you can make, is going to be equivalent to each other. So it allows...
Under which algebra? The Sitter algebra.
Yes. So you construct the... You have to keep...
You are exactly in a special idealized case in which
yes.
you can choose a solution of a classical solution.
Yes.
And define preferred observers
yes.
related to that.
Okay, so that is exactly
so
the question.
No,
so the
in that case, you don't even have the unphysical general covariance.
Yes, because you're breaking down to the isometries of the sitter. But the thing that I was curious about was whether or not the possibility of mapping sort of these different choices of clocks, as in different choices of basically a representation of the real line on your de Sitter algebra. Would that, if one extends this appropriately, let's say, to a
no, but then you don't even, that's even too exotic. If you are finding work in the approximation in which you have isometries, you have a given space-time, you have isometries for that space-time, therefore a preferred class of observers, then coordinate frames adapted to that isometry are physical, because they are identified by some physical field, which is the space-time geometry itself. And then the map between different observers and different physical frames is exactly the Lorentz algebra, the Sitter algebra. So you don't even need to go to that case, it's special relativity. It's a particular case of a physical covariance between frames in the case in which you have preferred observers. The problem arises only when you go to full dynamical context for space-time, geometry, and fields. You don't work with special solutions. And you don't want, at that point, you cannot work with coordinate frames anymore for all the reasons I mentioned. And you have to adopt some physical frame. There, the statement is, in general, we don't know if there is a map between the observables written in terms of different physical frames. If there is, we don't know if it is one-to-one or leaves out quantities. And then we don't know, and in fact, we do not expect that there are invariant elements under this map. Okay. So yeah, that's a special case, but it's so special that why do you want to go to the Sitter? Just take special relativity.
Okay. I have a general question about this project of undermining Humeanism and Humeanism. It seems to me that one way to read what's going on in the literature is that people try to accuse Lewis and Humeanism of being, in a vicious way, theory-laden. So, for example, the Humean mosaic is a spatial-temporal distribution of local particular facts, of space-time locality, theory-laden notions which get challenged in quantum gravity or quantum theory in general. But, right, I mean, both space-time and locality are very intricate concepts, which, apart from this theoretical dimension, we also have a very clear pre-theoretical or maybe even pre-epistemic dimension, right? And I'm just wondering whether you're right.
I agree on the very existence of pre-epistemic.
Sure, so let's just say pre-theoretical, right? Yeah, but full understanding. So, yeah, it seems to me whether it's just not, whether it's correct to read Lewis as being committed to some heavily theory-laden notion of space-time locality, and B, whether it's the best way to read Lewis. Right, so, and I took you to be objecting also to the notion of objectivity there, right? So I'm just thinking also whether a similar response on behalf of Lewis would be available in the case of objectivity by relying on some kind of folk notion rather than these theory-related notions. So these are just a couple of thoughts I had. Yeah, sorry.
So what was the question? So the question was...
I was trying to give an answer on behalf of Lewis to these objections.
Is that? You cannot do that.
Sorry?
It's unfair. Okay. Yes, one answer by Lewis was the one I mentioned about quantum mechanics, that he simply would not take on board a suggestion from quantum mechanics just because.
So okay, so say we discover quantum gravity tomorrow, right? I mean, it's not the case that people will suddenly be late for work or just confuse left and right because the concept of space-time has crumbled, right? We'll just problem is the Lorentzian manifold of general relativity. And maybe isn't it for Lewis just to kind of rely on the spatial temporal mosaic in some kind of...
yeah, I understand, but you know what is the problem with that, in my view? That there is of course a level in which, regardless of what even special relativity says, a number of spatial temporal concepts are our common sense. And we live our life with those. And so if that's what makes you say that those concepts are therefore fine and enough for understanding the world, first of all, for coherence you shouldn't call yourself a naturalist. And okay, fine, you can just say, you know, I don't care what science says is more fundamental, what is the more general case, stick with my common sense. Second, you have a bunch of issues because a number of things that were common sense some years ago, more or less, are not common sense anymore. Second, there is the general empirical challenge that common sense is in fact very theory-laden. You're just adopting a particular theory that explains your common sense in terms of some concepts. And that theory is subject to revision constantly. Third, science not only gives us new theories for accounting for experiences, but also gives us new experiences. Your concept have to follow, or at least be adapted. So, no. I don't find that line of reasoning particularly compelling. And of course, as I said, most of what I said, you can find objections, other ways of looking at things, even comparing with the same theories, with the same facts. Of course, no pretension of having said something clearly true. But if they're false, it's not because we are fine with common sense.
All right, I'm aware that there are further questions in the room, but since we're already 10 minutes over time, I'm afraid that they will have to discuss over lunch or maybe dinner. But first of all, please join me in another round of warm applause for Daniele.